Dear students, as part of this paper, in this module, we will be focusing on different types of growth rates. When we want to project population, there are various methods. So, let us discuss in this module. The major learning objectives of this module are to know about the population growth and the related factors, the arithmetic growth rate, geometric growth rate, exponential growth rate and logistic growth rate. These are the various methods through which we can estimate the population. Population projections are estimates of the population in the future. They are typically based on an estimated population consistent with the most recent decennial census and are produced using the cohort component method. Projections illustrate possible courses of population change based on assumptions about future births, deaths, net international migration and domestic migration. In some cases, several series of projections are produced based on alternative assumptions for future in the areas of fertility, life expectancy, net international migration and for state level projections, state to state or domestic migration. While projections and estimates may appear similar, there are some distinct differences between the two measures. Estimates are for the past and present, while projections are based on assumptions about future demographic trends. Estimates generally use existing data collected from various sources, while projections make assumptions about what demographic trends will be in the future. Data users may find both an estimate and a projection available for the same data, for instance July 2011, which may not agree. In such cases, estimates are the preferred data unless the user's objective is to compare the number with others in the projected series. In the cohort component method, the components of population change, namely fertility, mortality and net migration, are projected separately for each birth cohort, that is persons born in a given year. The base population is advanced each year by using projected survival rates and net international migration. Each year, a new birth cohort is added to the population by applying the projected fertility rates to the female population. Population data is available by various characteristics and they can be grouped around the topics which are presented below. Let us focus on aging and population structure. Based on the data available, the aging trends can be followed throughout the past decades. Information on age groups and their share in the total population are available by country and also at aggregate level. Indicators such as the age dependence ratio are calculated on the basis of the population structure. The other aspect is about population characteristics. Population figures by education attainment, marital status, citizenship and country of birth are available. The characteristics of the population can be followed also by citizenship and country of birth. Data availability is subject to the completeness of reporting by the countries under focus. Next aspect is about population density. The surface area is used to calculate population density in each region under focus. Next is about population growth. It refers to the manner in which the number of individuals in a population increases or decreases with time. This growth is controlled by the rate at which new individuals are added to the population, the birth rate and the rate at which the individuals leave the population, that is the death rate. The number of children a parent gives birth to is usually referred for calculating the birth rate. If all individuals in a population have 2 children, the birth rate would be 2 for instance. However, it is not necessary for the birth rate to be a whole number such as 1, 2, 3, etc. For example, if half of the individuals of the population have 2 children and the other half have 3, then on an average the birth rate will be 2.5. Likewise, if the population consists of equal number of males and females, and if the females give birth to 3 children each and the males 0, then the average birth rate of the population will be 1.5. One of the greatest dangers the planet Earth faces today is that of overpopulation by humans. Since the beginning of human history, our population has been growing exponentially. However, there is now little additional land that can be put into use for food production, and our wastes are rapidly polluting the environment. Unless major technological breakthroughs are made, we are close to their carrying capacity. Compounding the problem is the fact that our average birth rate is still very high, that is greater than 2.0. It is possible we will overshoot the Earth's carrying capacity and for the first time in recorded history have massive population decline brought on by disease and starvation. The decrease in birth rate needed to avert a disaster is not large, but it is one that everyone needs to work on. Given this scenario, it is very important to focus on the different modules that needs to be considered while we are projecting the population growth. As we discussed, there are 4 models of population growth, namely arithmetic change, geometric growth, exponential growth, logistic growth. Let us discuss in detail each of these models and how they are relevant and how they have to be used while projecting the population. The arithmetic change, it is the same as the simple interest, whereby interest is paid only on the initial sum deposited, that is the principal amount, rather than on accumulating savings. 5% simple interest on rupees 100 for instance merely returns a constant of 5 rupees interest every year. Hence, the arithmetic change produces a linear trend in population growth following a straight line rather than a curve. The arithmetic growth rate is expressed with an equation, that is R is equal to Pt minus P naught divided by T divided by P naught into 100. Geometric growth. Geometric population growth is the same as the growth of a bank balance receiving compound interest. According to this, the interest is calculated each year with reference to the principal amount plus previous interest payments, thereby yielding a far greater return over time than simple interest. The geometric growth rate in demography is calculated using the compound interest formula. Under arithmetic growth, successive population totals differ from one another by a constant amount, whereas under geometric growth they differ by a constant ratio. In other words, the population totals for successive years form a geometric progression in which the ratio of adjacent totals remains constant. A geometric series is one in which the population increases or decreases at the same rate during each unit of time, usually a year. If this constant rate of change is represented by R and the initial population is represented by P naught, then after T years the final population is given by the following equation: Pt is equal to P naught upon multiplied by 1 plus R power T. So that the geometric growth rate R can be expressed in the following equation: R is equal to square root of Pt by P naught of t minus 1. However, in reality population change may occur almost continuously, not just at yearly intervals. Recognition of this led to a focus on exponential growth, which more accurately describes the continuous and cumulative nature of population growth. Let us discuss in detail about exponential growth. If a population has a constant birth rate through time and is never limited by food or disease, it is known as exponential growth. With exponential growth, the birth rate alone controls how fast or slow the population grows. Consider a small population of some species let loose in a large area. For example, in October 1859, Thomas Austin released 24 rabbits on his farm in Australia. This population eventually grew to over 600 million. We let t represent time measured in years. If we were considering a population of whales, we might measure time in decades, while for bacteria, we would measure time in hours or minutes. We let P of t would be the population at time t. Again, we might measure P as the number of individuals for whales or thousands or millions of individuals for rabbits or people. We could also let P represent a population density. That is, we could let P be the number of rabbits per square kilometer or square meter. So, fractional values of P are allowed. As the notation suggests, we think of P of t as a function of t. Our goal is to be able to predict a value of P upon t for any time t. We could just write down a guess for a formula of P of t, but that is not much more satisfying than just guessing the values of P of t. Instead, let us think a little bit about biology. What do we know about rabbits? Well, rabbits do what they are famous for and beget more rabbits. The more rabbits you have this year, the more baby rabbits you will have next year. So, the basic biology of rabbits tell us not what the population of rabbits is, but rather how the population changes. Our models for population size will be based on rules derived from how the population changes. We start with the simplest aspect of population change and make some explicit assumptions about how they work. Number 1. The number of birds between time t and time t plus 1 is proportional to the size of the population Pt at time t. That is, there is a constant b higher than O such that the number of birds between time t and t plus 1 is b into P of t. Number 2. The number of deaths between time t and time t plus 1 is also proportional to the size of the population Pt at time t. That is, there is a constant d greater than 0 such that the number of deaths between time t and t plus 1 is d multiplied by P of t. Clearly, these are just the most basic assumptions on how any population might change. There are many factors that affect births and deaths. These include external factors like the weather and factors that depend on where the species is on the food chain. However, we start simple and ignore all other mechanisms of population change. Now, we must turn these assumptions into statements that we can use to compute future populations. Putting our two assumptions together, we can say that the population at time t plus 1 is the population at time t plus the births between t and t plus 1 minus the deaths between t and t plus 1. We can write this on one line as population at time t plus 1 is equal to population at time t plus births t to t plus 1 minus deaths t to t plus 1. Now, our assumption says that the births of time t to t plus 1 are given by b p of t, while the deaths are given by d p of t. Hence, we can shorten the sentence above with a notation writing it as p of t plus 1 is equal to p of t plus constant B of Pt minus constant d P of t. This completes our translation of the assumptions into a formula. We can now use the algebra you learned long ago to simplify things even before. By factoring out P of t on the right, we get P of t plus 1 is equal to 1 plus B minus d of P of t. We can consolidate a bit more by letting k is equal to 1 plus B minus d, and calling k the growth rate constant. Our model can now be written in very efficient form like P of t plus 1 is equal to k of P of t. If there are more birds than this, that is B greater than d, then k is greater than 1 and the population at time t plus 1 is larger than the population at time t. If we know the population at time t is equal to 0, then at time t is equal to 1, we have P of 1 is equal to k of P of 0. And at time t is equal to 2, we have P of 2 is equal to k of P of 1, which is equal to k of k P of 0, which is equal to k 2 P of 0. And at times t is equal to 3, we have P of 3 is equal to k of P of 2, that is k of k 2 P of 0 is equal to k 3 P of 0. You can see the pattern developing here. A proof by induction shows that the general case as follows: P of n is equal to k P of n minus 1, that is equal to k of k n minus 1 P of 0, which is equal to k of n P of 0. And we have a formula for the population for all future times n, provided we know the population at time 0. This type of model is called an exponential growth population model, because the population P of n is an exponential function. Let us discuss the other growth model, that is logistic growth. In a population showing exponential growth, the individuals are not limited by food or disease. However, in most real populations, both food and disease become important as conditions become crowded. There is an upper limit to the number of individuals the environment can support. Ecologists refer to this as the carrying capacity of the environment. Populations in this kind of environment show what is known as logistic growth. In the image below, the carrying capacity is the maximum number of individuals within a species an environment can maintain. Under A exponential, that is unrestricted growth, where the population size depicted in y axis and the time in x axis clearly gives the exponential growth, where the growth rate of population accelerates. In the case of the other model, that is logistics or restricted growth, the rate of accelerates to a certain point, that is point of maximum growth, and then the rate slows down. That is it is taking a carrying capacity of environment which is below, under which the growth rate occurs. The exponential equation is a useful model of simple populations, at least for relatively short periods of time. For example, if a laboratory technician needs to know when a bacterial culture reaches a certain population density, the exponential equation can be used to provide a prediction as to exactly when that population size will be reached. Another example is in the case of agricultural pests. Herbivores are always potentially major problems for plants. When the plants subjected to such outbreaks are agricultural, which is to say crops, the loss can be very significant for both farmer and consumer. Thus, there is always pressure to prevent such outbreaks. Since WWI, the major weapon in fighting such pest outbreaks, has the chemical pesticides such as DDT. However, in recent years, we have come to realize that these pesticides are extremely dangerous over the long run, both for the environment and for the people. Consequently, there has been a movement to limit the amount of pesticides that are sprayed to combat pests. The major way this is done is to establish an economic threshold, which is the population density of the potential pest below which the damage to the crop is insignificant. That is, it is not really necessary to spray. When the pest population increases above that threshold, the farmer needs to take action and apply some sort of pesticide or other means of controlling the pest. Given the nature of this problem, it is sometimes of utmost importance to be able to predict when the pest will reach the economic threshold. Knowing the R for the pest species enables the farmer to predict when it will be necessary to apply some sort of control procedures, which is depicted as a model where in the x-axis the time of planting starts and time to apply the control, that is according to model 1, which creates the economic threshold as a base under which these different models can be presented. The exponential equation is also a useful model for developing intuitive ideas about populations. A classic example is a pond with a population of lily pads. If each lily pad reproduces itself, 2 pads take the place of where 1 pad had been each month, and it took say 3 years for the pond to become half filled with lily pads. How much longer will it take for the pond to be completely covered with lily pads? If you do not stop to think too clearly, it is tempting to say that it will take just as much time, say 3 years, for the second half of the pond to become as filled as the first. The answer of course is 1 month. Another popular example is the proverbial ancient Egyptian or sometimes Persian mathematician who asks payment from the king in the form of grains of wheat, sometimes rice, 1 grain on the first square of a chessboard, 2 grains on the second square, and so forth until the last square. The pharaoh cannot imagine that such a simple payment could amount to much and so agrees. But he did not fully appreciate the exponential growth. Since there are 64 squares on the chessboard, we can use equation 2 to determine how many grains of wheat will be required to pay on the last square, or raised to the 64th power, a lot of wheat indeed, certainly more than in the whole kingdom. These examples emphasize the frequently surprising way in which an exponential process can lead to very large numbers very rapidly. The explanation here is as follows. Constant growth in a time frame, for example, on an annual basis, population grows in the same amount, such as in the year say 2000 population was 100, in year 2001 population was 101, in year 2002 population was 102, in year 2003 population was 103, in 2004 population was 104, in the year 2005 population was 105. In any year population increases only 1 compared to the previous year, therefore population growth rate is constant and 1% per year. In the case of the exponential growth, starting population was 100 in 2000 year, population next year was 103, population in 2002 becomes 107, population in 2003 becomes 112, population in 2003 was 118, population in 2004 was as high as 125, population in 2005 it becomes furthermore to 133. The population growth is 4.46% annually, and that is called exponential growth. Let us focus on logistic growth. Logistic growth is similar to the exponential growth, but in this case there is an upper limit such as the carrying capacity. For example, human population increased considerably in the world over the past 80 years, but population growth rate decreased remarkably over the past 15 to 20 years. The carrying capacity is estimated to be 10 or 15 billion. It can be sometimes projected as 9 billion. The logistic growth is similar to S curve. You will also find exponential growth opportunities in daily life. For instance, investments and wealth. Thanks to the power of compound interest, your retirement savings start out at a small treasure in the early years, but balloon in size during the final decade or two of savings. Email subscriptions and website traffic New websites receive just a trickle of traffic here and there, but as the weeks and months roll on, those trickles can build into a rising river of visitors and subscribers. Similarly, entrepreneurship and business growth, the assets that you build for your business stack on top of one another and revenue compounds throughout the life of a successful business. Similarly, social media followers, when you only have 100 followers, getting another 100 followers may take 6 months. Once you have 1000 followers, however, getting the next 100 may only take 1 month. Once you have 1 lakh followers, getting another 100 probably takes 1 day. Your growth rate snowballs. Let us discuss about various challenges of each growth curve. Neither type of growth is good or bad. These growth patterns are simply the way certain things work. However, it is important to understand the growth pattern of your task so that you can set your expectations appropriately. Do not expect exponential returns when you are playing a logarithmic game. Similarly, do not expect quick wins when you are building something that has an exponential curve. When dealing with large logarithmic growth, the challenge is to avoid feeling discouraged as your improvements decrease. Improvement will come easily in the beginning and you will become accustomed to enjoying small wins each day. Soon, however, those small wins will become smaller. Logarithmic growth requires you to have the mental toughness to play a game that will, by definition, become more challenging to win as time goes on. You will feel like you have plateaued. You will question yourself and your abilities. If you want to succeed with logarithmic growth, you have to learn how to fall in love with the boredom of doing the work if you want to maintain consistency as your improvements dwindle. When dealing with the exponential growth, for instance, the challenge is to continue working throughout the early period when you have little or nothing to show for your effort. Exponential growth requires you to be remarkably patient and diligent, often for years or decades before enjoying a significant payoff. There may be 10 years of silence before you hear the sound of success. Equally important, you need to give your best effort even when you are getting average results. Exponential gains only result from sustained effort in the early years. Overall, in this module, we are able to discuss in detail about various models that are commonly used while attempting to estimate the population and for the future estimates for the population and population growth. So, my dear students, this will enable us in what context, with what assumptions we have to estimate the population for future growth, so that we will have a reasonable level of understanding about what is going to be the future scenario when we are seeing the population of a particular region in a particular time periods. Thank you.